and when you will be going through the different aspects, you'll be coming across the way by which the changes in the properties and the structure will be taking place either in the weld or in the heat affected zone in the solid state joining of the metals. So you know that the recrystallization temperature, the temperature at which your newer grains will be found on heating above a certain temperature, and that temperature again depends on the kind of the metal. Apart from this, so that temperature at which you get the newer grains being formed, or the temperature at which recrystallization is taking place, say it ranges from say about 0.3 to 0.6 times or higher, certainly it can be. uh, and another thing, this temperature is affected, like the recrystallization temperature is affected by the two things. One is the deformation or the strain condition, okay, and the second is the purity or the, like say, the alloying concentration. Okay, so if you see this aspect in general, with the increase of the increasing deformation reduces the recrystallization temperature, RT. Okay, and the second is the increasing purity decreases the recrystallization so the TR, or recrystallization temperature, decreases with the increasing purity, which means with the alloying, with the increase of alloying, there may be marginal increase in the RT. So these are the two different aspects. Why I am talking here? Because you know, in your solid state joining, either the interfaces are deformed or the weld nugget is deformed. So weld nugget will be experiencing the reduced recrystallization temperature. Okay, and so even with the little heat, you may get there is a possibility of the recrystallization of the metal or formation of the new grains. So like whether it is even the diffusion bonding will also be experiencing the micro level interfacial deformation, which may range say from 2 to 3 micrometer interfacial deformation. Say in your ultrasonic welding also it may be like say 4 to 5 micrometer both the sides, and in friction stir welding maybe like say the 5 to 10 mm also of the weld nugget zone. So the metal is being deformed heavily to the different magnitudes or to the different levels. Okay, and these deformation will be lowering the recrystallization temperature, and thereby it will be affecting the properties. And what you have seen is this, you see, with the recrystallization, your the kind of the change in properties that will be occurring, that is what you can easily understand. Okay, so here this another thing is the decrease in purity. So with the change of increasing purity decreases the recrystallization. So if it is just say pure iron, for which it is say 400 degrees centigrade, maybe aluminum say it is 150, I'm not 100% sure, but there are different values for the different metals. For copper it is 200 degrees centigrade. So the moment you go for alloying, there is a possibility that these temperature values may be little higher than these typical temperature values for pure metal. Okay, I hope this is a very simple thing about which you will be knowing. Like the work hardening or the strain hardening will be increasing the dislocation density, and because of that your strength and hardness both will be increasing, but at the cost of your ductility and mostly about the toughness as well. So what this is what you can see when a simple low carbon steel, when it is subjected to the different value of the deformation, that's cold working, to the different percentages, say 0%, 4% and 24%, the way by which the properties change. If you take any steel weld joint, when it is subjected to the deformation, when you take any steel or the metal, when it is subjected to the deformation, certainly it will be experiencing the change in the properties, and this is just an indicative of your strength has gone up with the, say 4% of the cold working and reduction in the ductility. Okay, say earlier it was say 23%, now say it is around say 18 or 20, and this is further reduced with the increase of the cold working. Okay, so the metal, say if you take the steel weld joint and develop, say using the solid state joining technique or using say the ultrasonic welding where micro level deformation is taking place at the interface, in all these cases you will notice that the hardness distribution at the interface goes in like this, indicating the, like say it goes in like this. So this even if there is a same phase, but you may see the uptrend in the weld nugget zone or the joint interface area, and this is attributed to the kind of the deformation that will be taking place. There is a possibility, like if the rise in temperature is limited, then it is good. If the rise in temperature is more, then the effect of the cold working can be negated or can be reduced. So when there is, like say rise in temperature is more or rise in temperature is less, so for low temperature case or for high temperature case, you may get this kind of situation. So high temperature will be causing the recovery and the recrystallization, the kind of things, and that's why you will be getting the reduced increase in the hardness and the strength. Okay, so these are the kind of changes you can see. As the cold working is increased, yield strength increases, the tensile strength also increases, and then there is a decrease in ductility. So this is what you can see, the decrease in ductility. And so we'll go once again. So there is a increase in the yield strength, ultimate strength, and then decrease in ductility. This is what you can see using these lines. Just for an example, if you see when the copper is taken, the way by which the properties will change for copper with the increasing percentage of the cold working. Okay, so let's say the copper, when it is worked, so yield strength increases say from around 150 value to around say 350 value with the change of the percentage of the cold working for the copper. Likewise, there is a change in the tensile strength and reduction in the percentage elongation. So depending upon, so this change is related with their ability to work harden. Different metals respond differently for these kind of the changes. So that is what you can learn from your these curves, the kind of the way by which the two metals will be responding, A and B. So in this case, the work hardening is very limited beyond the yield point, and in another case the work hardening is significant. So two metals respond differently for the cold working and the deformation. So depending upon the metal which is being subjected to the solid state joining, experiencing the deformation, the kind of change that will be taking place in the yield strength, tensile strength, and ductility, that may change significantly depending upon its work hardening capability. So for steels it is huge, likewise for copper, but for aluminium it is limited, and that is why, and this work hardening capability is usually linked with the stacking fault energy of the metal, of a particular metal. Lower is the stacking fault energy, higher will be the work hardening tendency of the metal. So high work hardening tendency metals like cobalt, austenitic stainless steel, super alloys, they create a lot of problem during the machining because of this hardening tendency. Cold worked metals will be experiencing the effect of heat more badly as compared to the other metals. So this is an important thing. Let me talk about this. Okay, so this is let's say, right? Okay, so here your annealing temperature, right? And let's take the two metals strengthened by the different mechanisms when subjected to the same annealing temperature. Two metals strengthened by the different mechanisms exposed to the same annealing temperature. So one which is uh, strengthened by the mechanical working will be responding like this. This is what you have seen just now in case of the copper or in case of steel. Okay, say if the metal has been strengthened by the other than this kind of the mechanism. Okay, so this large difference you can see the temperature at which the recrystallization is taking place, the recrystallization temperature. Here you can write is say yield strength of the metal. But if you take a metal which is not only this strengthened by the cold working or not at all strengthened by the cold working, the annealing temperature may not be having that much effect. Say under identical conditions, if you are using the annealing temperature and one is say dispersion strengthened, okay, or transformation hardened, in those cases you may find that although there is a change, but it is very marginal. So the kind of the drop which is taking place above the recrystallization temperature may not be huge. That will depend upon the relative contribution of the metal strengthening mechanism. Okay, say for dispersion hardening, the metal which has got its main strength due to the presence of reinforcing agents which are there in a metal, in those cases your metal may not be, the joint strength and properties may not be much affected by the heating of the metal above the recrystallization temperature. Whatever drop you will be coming across, that may be due to the minor loss of the work hardening effect which was there in a metal, because there is no commercial system which will be strengthened just by one mechanism. They will always be strengthened by the multiple mechanisms. Invariably you will find the effect of solid solution strengthening or grain refinement or work hardening, but relative effect of these may be negligible or very less. So whatever the effect of these mechanisms are there in a particular metal, only that will be neutralized or reduced as per the case or as per the way by which the metal is being subjected to the heat or the deformation. Okay. This will give you the more clearer picture for having the better understanding why in a joint, whether it is a joint of the different metals, like let's say we will be talking about the way by which the heat affected zone of the four types of the metals are affected, what kind of changes that will be taking place in the four types of the metals, means they are strengthened by, say, transformation hardening, work hardening, and your precipitation hardening, and say grain refinement. Let's talk about these four different types of the metal. If a metal has been strengthened by combination of all these, then you will notice that there is a combined change of the heat applied, or kind of increase in temperature which is taking place in the heat affected zone. So just for your understanding, here for plain carbon steel up to 730 there is no change in the phase, except that there is a recrystallization. So this temperature band from say 400 to 730 where new grains will be formed. So you can say that as a recrystallization temperature zone. Above that, let's say you take this system, okay, from this band, this range. So this is your intercritical, this is your lower critical temperature, and this is your upper critical temperature, okay, and the metal which is heated in between, this will be the intercritical. So this say maybe 890 or I'm in class now, maybe I'll talk later at 12 o'clock, okay. So this is your intercritical temperature range, and this is the range where you will be finding the very fine grain structure, okay. And when metal is heated above this 910 or 900 up to this, so this is the another band where you will be getting the austenitic state. This is the range where you will be finding the coarsening. Higher the temperature, greater will be the coarsening of the grains. So if you expose at 1000, the grains will be say little coarser, maybe say 12 micrometer. If you expose the same at 1300 degrees centigrade, they will be further coarser, say 15, say 18 or 20 or 25 micrometers. So the grains will get coarsened, and whatever you will be getting here, the coarse grained austenite will be producing the coarse grained pearlite or coarse grained martensite accordingly, okay. Now coming to this zone where you have both solid as well as the liquid, that is the you can say lower side you have solidus and upper side you have liquidus. So both the metal or the zone which is mixed of both, that will be leading to the formation of the partial melting zone. So in a typical steel having a little wider solidification temperature range, you will be getting all these zones starting from base metal to the recrystallization zone, fine grained zone, coarse grained heat affected zone, and partial melting zone. Now depending upon the composition, if this carbon content is little more, you may get the martensite very easily, or it may be mixture of the martensite and pearlite. Here you may get the fine pearlite, okay, or fine martensite as well. Recrystallization zone may just with the newer grains of the like ferrite and pearlite, okay. So the point here is which kind of the phases will be formed, that is a different thing, but these are the different zones that will be formed in a typical transformation hardening metal like steel, starting from your recrystallization zone to fine grained zone, coarse grained zone, and then partial melting zone. Each one, so whether it is solid state joining or your fusion joining, in all these cases, depending upon the rise in temperature, you will have these formation of these zones, okay. So if the temperature is limited to say 1000 degrees centigrade, then you may have just coarse grained zone, fine grained zone, and recrystallization zone. if the temperature is limited to 800 degrees centigrade, you may have just fine grained zone, no coarse grained zone, okay, and refined grained zone and recrystallization zone. So this is important to be seen. If you take any metal and measure the temperature next to the weld nugget area and see what is the peak temperature. So if you are aware of the peak temperature, you can easily anticipate or you can estimate the kind of the grain structure or kind of the phases which will be there in a particular region, in the coarse grain zone, heat affected zone, fine grained zone or recrystallization zone. So whether the temperature here is 1300 or 800, that will determine what you will be getting in this area. Okay, so this is so this is how you can link the rise in temperature in the solid state joining in a transformation hardening systems like iron carbon systems, and the way by which the changes in this one will be taking place. Okay, the changes in the vicinity of the metal that will be taking place. Okay, so I hope this is clear. Anybody can respond, is this clear? Okay, so because in solid state joining you may notice that rise in temperature is not significantly high, so accordingly you will be getting that formation of the different phases or the different zones. This is one story of the transformation hardening metals. Now if you talk of the other kind of metals, it will be different. Let's say this is the work hardening metal. Metals strengthened primarily by the work hardening, and in aluminium alloys like say aluminium, magnesium and manganese, one this kind of typical system which is strengthened primarily by this. And there are other systems like high manganese steels. So those also get lot of this strength from the deformation and work hardening. So you see, the base metal which has been strengthened by the work hardening means it is full of the dislocations, right? And if you notice the different zones will be experiencing the different temperatures. Say take 0.1, 4, 0.3, 0.2 and 0.1. What kind of peak temperature they will be experiencing? 0.4 very low, 0.3 little high, 0.2 further high, and 0.1 is maximum in vicinity of the weld nugget or the joint interface. Okay, so this is the peak temperature is high, so you will notice that the recovery will be taking place significantly and in very short time. Okay, so the complete recovery you will be noticing here, not just recovery, formation of the newer grains, even coarser grains. So you will notice that there is a complete recovery. There are three things that will be happening at location say 1 and 2. So this complete white location, what you can see here, just a minute. At location 1, this is the location 1 where your partial melting is taking place, because this zone may be falling in the mushy zone like this typical aluminium alloys. This it goes in like this. Okay, so this is the liquidus and this is the solidus. You have got a range. This is two-phase zone, right? This is the two-phase zone. So you may notice the temperature here is say this temperature is around 670 and this temperature is 550. So any zone which is falling in this band of the temperature, that will have the two phases, and that will be leading to the formation of the partial melting zone. Next to that is the zone which is being heated very close to the solidus. So that will be experiencing the complete recovery 1, recrystallization another, and the grain growth as well, because the temperature is too high. So recovery, recrystallization and grain growth all will be experienced in the zone 2, right? And if you see the zone 3, which is experiencing little lower temperature, you will notice that the recovery is partial, because still you can see few dislocations here and there. Recrystallization may also be limited. On the other hand, the zone which is far away from the weld nugget area, that is being heated for further lower temperatures, and you will notice that there is no recovery, no recrystallization in the zone 4. Okay, so that's how you can say the zone 4 is falling in an unaffected base metal, then the partial recovery, partial recrystallization, complete recovery, complete recrystallization, and say partial melting. So this is the kind of the structural change that will be experienced in the work hardened metals. Now you know that when the base metal is having large number of the dislocations, then the hardness is more. Hardness is coming down gradually as soon as there is a recovery, or although recovery is partial, then there is a complete recovery like this. So this is the complete recovery zone, this is the partial recovery zone, and then this is the unaffected base metal. So the loss of dislocations will be leading to the reduced hardness, reduced strength, and so this will be leading to the formation of the weak zone. On the other hand, if it has been formed by the solid state joining process, the deformation may cause again the jump in the hardness, because this is the zone that will be experiencing the work hardening effect. And if it has been developed by the fusion kind of process, then everything will be getting lost, only you will have the cast structure. Okay, so this is the story of the heat affected zone of the work hardened metals. Now if you talk of the precipitation hardening metals, in precipitation hardening metals, what you will have, let's take like there are number of systems like aluminium, copper, aluminium, magnesium, silicon, aluminium, zinc, magnesium alloy. So say 7000 series aluminium alloy, or 6000 series aluminium alloy, or 2000 series aluminium. These are the three series which have been developed using the precipitation hardening approach. Okay, and if you take the precipitation hardening kind of the mechanism kind of thing, then you will notice a typical diagram of this kind. Okay, so this here you may have different precipitation curves or lines like this, right? And this is the solvus line. So here your homogeneous kind of thing. So if you take your alloy composition is here, right? So your the phases, the hardening phases, as soon as they are heated above a particular temperature, they start getting dissolved, and they are completely dissolved as soon as you reach above the solvus line. So here this is the alpha phase. Everything is getting dissolved in this zone. So all fine precipitates have got dissolved. So as soon as you get you are crossing the particular line above which the precipitates getting destabilized, there may be different types of the like GP zone 1, GP zone 2. Those kind of the things will be getting destabilized with the increase of temperature. So and eventually it will be forming the homogeneous solid solution at a higher temperature. Now if you see here, the base metal which is strengthened by the precipitation hardening, in the base metal it is full of fine precipitates, you can say, and these fine precipitates are contributing towards the desired strength of the metal. So your hardness is really quite good in this zone. As you move towards the joint interface, what you are noticing, there is a rise in temperature as you approach. This is typical of weld thermal cycle. As you approach towards the joint interface or weld nugget area, your temperature rise will be there. Increasing temperature will be causing the dissolution or overaging of these precipitates. There are two things which are possible. Because it was strengthened by the precipitation hardening, so you have already got it aged to such an extent that there are sufficient precipitates. The further heating to the higher temperature for longer time will be causing the overaging. Overaging means the loss of certain precipitates and coarsening of the existing precipitates. These are the two changes that will be occurring. And further higher temperature will be leading to the complete dissolution of these precipitates. Okay, so there are three changes which are taking place. Initially you have the base metal having the fine precipitates, then these are getting overaged, then these are getting dissolved. Okay, and you are left with the, like say, homogeneous coarse grained the alpha matrix only. All precipitates have got lost. Okay, so the something which was hard due to the presence of precipitates, it will start losing the strength as you approach towards the weld nugget area. This is the loss of strength primarily due to the loss of precipitates, and then you reach to the zone further down. So here further down or decrease in the hardness is being attributed to the coarsening and the reversion. So this is the minimum hardness zone of the heat affected zone. So this is what we can say, this is the softening or the weakening of the HAZ. Softening or the weakening of the HAZ in precipitation hardening alloy is primarily caused by the overaging, reversion or dissolution of these precipitates, and then grain coarsening. Here very coarse grain, reversed zone where complete dissolution has taken place, or the overaging. So these are the three main causes because of which softening of the precipitation hardening alloys take place. Okay, I think that's so in order to restore the property similar to the base metal, there are two ways. You go for the PWHT. So there are two ways, either it will go for like T6 kind of condition or T4. Just solutionize and put it at under the welding condition. They are naturally aged metals also, like the aluminum, zinc, magnesium alloy. You weld it, after a week or so it will regain its strength. So that is a different thing, but it is not so for 2000 and 6000 series aluminum alloys. Okay. Coming to the grain refinement, those which are strengthened by the grain refinement, you see their story. Okay. So I think this is not indicating. This one will be more helpful to explain what I want to say. Let's talk about this. This is what I have just said, like the zone which are at different distances from the weld nugget area will be experiencing the different temperatures. So increasing temperatures at location 1, peak temperature is high, location 2, peak temperature is somewhat lower, further lower. So, and beyond this, the base metal is really not affected, so your strength is really good. So at 3, there is a marginal drop, there is a significant drop, and further drop at location 1. So these you can attribute as a loss of dislocations or the loss of the precipitates, overaging, grain growth, all these. Okay. Now what happens when you apply the different amount of heat? Like say, if you have applied the heat of 0.2 kilojoule per mm or 2 kilojoule, 0.5 kilojoule per mm or 2 kilojoule per mm. There is a lot of difference in this. When you apply less heat, what you are getting, very small zone nugget size, very narrow heat affected zone. When heat is increased, nugget size increases and your HZ size also increases. So these will keep on increasing. The widths will keep on increasing. Okay, and that is what you can see here. The minimum hardness zones are also increasing. The width of the minimum hardness zones are also increasing. And this is attributed to what? This is being linked with the weld thermal cycle. At point 1, very close to low. So this is what you have. When you have low heat input, the thermal cycle is like this. When little higher heat input, thermal cycle is like this. Further higher heat input, thermal cycle is like this. So what is happening here? You can see when the thermal cycle is corresponding to low heat input, your grain size is very fine because high temperature retention period is low. When heat input is more, high temperature retention period is longer. That is what you can see. And further high heat input, the high temperature retention period is further longer, even for the same peak temperature. Okay, so there will be enough time for diffusion to take place at a higher temperature and contribute towards the coarsening of the grains, towards the softening or development of the soft phases due to the lower cooling rates, higher temperature retention for longer time. Okay, so higher heat input means the lower cooling rates, higher and longer high temperature retention period, higher temperature and longer high temperature retention period. So these are the two factors which will be working against time, temperature and the time. Both will be compromised with the increase of heat input, and that is why we want, it is very easy. When you have coarse grains, the properties will be further lower. That is what you can see here. The minimum hardness is also decreasing. Minimum hardness is more. So say for the maximum heat, the minimum hardness is here. For minimum heat, the hardness is higher, and for medium it is here. So that's what you can see in this plot as well. That's what you can see here. Okay, so minimum hardness, the minimum hardness is here for minimum heat input, then here for somewhat more heat input, and the minimum hardness is further lower for further higher heat input. Okay, so that's how you can relate with the kind of changes which will be taking place in these 4 types of the heat sensitive metals: grain refinement, work hardened, transformation hardened and precipitation hardened. So these are the kind of changes which will be experienced by the metals due to the heat that is being delivered during the solid state joining. Okay, so this is where I will stop. This is just one aspect about which I have talked. So now I hope you can relate or you can understand how the HAZ of the different metals will be affected by the heat which is being applied during the solid state joining. Okay, and about the weld we have already talked a lot earlier. So that's how I think I complete the last section of the first chapter. Okay, so next lecture onwards we'll be taking up the new lecture, new topic or new chapter.